Hey, here we are again, the final lesson from section 1.6. We have learned so far how to translate the graph of a function, how to reflect the graph of a function, and now what we're going to learn is how you stretch or compress the graph of a function, either horizontally or vertically. Now, I imagine this is going to take a little explanation for you, and so I'm going to try to give that to you. When I'm talking about stretching or compressing a graph, let me just make a pretend graph right here. Let's say this is the graph. Ooh, I don't want to use that. I want to use the pen. Let's say that this is the graph of the function. There's the y-axis, the x-axis, and let's say I have that graph right there. Well, if I compress the graph, the effect that that's going to have is it's going to make the graph appear wider. So it would look like this. If we're talking vertically, that's a vertical compression. Whereas if I stretch the graph, what it's going to look like is you're taking hold of these little things right here, the handles, so to speak. And you're pulling them kind of like puppet strings. And it makes the graph get a little taller like that. Okay, that would be a vertical stretch. And you're going to see what a horizontal stretch and a horizontal compression is as well. But first, let's get right into the rules for stretching a graph. And we're going to look first at the rules for horizontal stretch or compression. Just like with reflections, what we're doing in order to stretch a graph or compress it is we're using multiplication. But instead of multiplying by -1, we're going to be multiplying by some other value. Here you see, to stretch or compress a function horizontally, what you do is you simply multiply its input value by some number q. Alright? And multiplying by that number q will stretch the graph by a scale factor of 1 over q. So if you multiply the input value by 3, that will stretch by a factor of 1/3. If you were to multiply by 1/5, that would stretch it by a factor of 5. Alright, let me kind of write that. If I had a function y equals, let's just say x squared, if I were to multiply the input value by 3, that would stretch by a factor of 1/3. If I were to multiply the input value, say, by 1/5, that would stretch the graph horizontally by a factor of 5. And you're going to see how this works, but with a different type of function actually. Let's go to the graph. By far the best function I can think of to show you a horizontal stretch or compression is a trigonometric function, either y equals sine x or y equals cosine x. What I'm going to do is I'm going to go with y equals sine x. And so I'm going to go ahead and type that into the input bar, and you can see what that graph looks like. Okay, there's the graph of y equals the sine of x right there. So you got that little wave function going. You've seen that graph on a couple of quizzes at this point, haven't you? Alright, it's one that's very useful for analyzing transformations and other types of things with functions. Okay, now what I'm about to do is I'm about to make this graph into y equals, let's say, the sine of 3x. I'm going to multiply the input value of that function by 3. And what you're going to see is that's going to stretch the graph. Actually, it's going to look like a compression. And it's going to do so by a scale factor of 1/3, the reciprocal of what we multiply the input value by. Essentially, then, you're going to have, for every little part of the graph right there, or every complete wave, you're now going to have 3 waves. Watch. Pretty cool, right? Now let me illustrate what I said a second ago about this making 3 waves for every 1 wave that was there before. I'm going to trace the portion of the original graph from the first, from where it started at the origin, through what you call a complete cycle. There's one complete cycle, and you can see how it's going to start that same pattern over again afterwards. And then I'm going to go ahead and copy the other one and show you that it had 3 complete cycles in that same time span. So there's one complete cycle, there's the second complete cycle, and there's the third complete cycle. That was stretching by a factor of 1/3. And really, if you're stretching by a factor that's less than 1, that's a compression, right? It made the graph narrower, kind of scrunched it together. Well, that's a horizontal compression. And what we want to look at next is how do you stretch a graph vertically. Now, you might remember with the other types of transformations, we kept altering whether we were changing the input value or changing the output value, and that determined whether we translated horizontally or vertically, whether we reflected in the x-axis or the y-axis. That also determines whether we stretch horizontally or vertically. When we want to do a vertical stretch, what we're going to do is we're going to multiply the output value f of x by some number p. Okay, that could be multiplying it by 5, could be multiplying it by 2/3. And whenever you do that, that's going to stretch the graph of f of x vertically with a scale factor that's actually equivalent to whatever you multiply it by. In the last instance, whenever we did the stretch, the scale factor was reciprocal of whatever we multiplied the input value by. If we multiplied by q, the scale factor was 1/q. For a vertical stretch, the scale factor is exactly what you multiply the output value of the function by. So, if I were to take a function y equals the absolute value of x, no, let me put an actual absolute value sign. I was trying to write it like I would into my graphing program. If I wanted to stretch that vertically by a factor of 2/5, I would simply multiply the output of the absolute value of x by 2/5. I'm going to show you this once again with that cosine graph, actually as a sine graph, and it's just really great for showing all kinds of stretching and compression. Let's go back to the graph. Here is the graph once again for y equals sine of x, and I want to show you how to stretch that vertically, which means that instead of multiplying the input value by some constant, what we're going to do is we're going to multiply the output value, what you get after you take the sine of an angle, by a scale factor. And let's say I multiply it by a scale factor of 4. Alright, and that will stretch the graph vertical by a scale factor of 4. The effect of that is going to be this. You can see currently how the lowest point on this graph is -1 and how the highest point is +1. Well, this is going to stretch it so that the highest point is at +4 and the lowest point is at -4. It's going to make it 4 times as tall, so to speak. Watch. Okay, there's the graph of y equals 4 sine of x. And just as I said, where the original function had a high and a low at 1 and -1 respectively, when we stretched it by a factor, vertically by a factor of 4, now the high and low points were 4 times as big as they were before. Now I want to show you, this is just a vertical stretch, it's not a horizontal stretch. If I were to trace the first graph, trace an entire cycle of the first graph, well, there's one cycle before the pattern begins again. And if I do the same thing with the second graph, you're going to see that exactly one cycle is still going to happen over that same time frame. But the peaks and the valleys got higher and lower, so that was a vertical stretch. And if I wanted to make it a compression, I simply would have multiplied by something like 1/2 instead of by 4. Alright, I'll show you that real quick. Okay, here's the same equation but multiplied by 2/3 instead of by 4, and you can see that the valleys and the peaks are 2/3 as high as they were compared to the original function. So that's a vertical stretch. Alright, we're going to finish this just like we did the translations and the reflections. We're looking back at example 14, and we're going to look at how do you stretch or compress a graph by a certain scale factor if all you're given is a graph. And what we're going to look at first is this part E. What if I were to try to take this function f of x and I were to try to graph 2 times f of x? Now, what you ought to realize here is that since you're multiplying the output of the function by 2, that's going to be a vertical stretch by a factor of 2. Okay? And so the result of that is it's going to take every y coordinate essentially and double it. 0, 0 is still going to stay in the same place, but the point 2, 2 would stretch to 2, 4. The point 4, 2 would stretch to 4, 4. The point 6, 4 would stretch up here somewhere to 6, 8. You see the graph stretches horizontally in the exact same fashion that it did, but it just got twice as tall as it was before. That's a vertical stretch. Now, the example 14 in the textbook doesn't have an example of a horizontal stretch, yet I want to show you one anyway. So let's clear this, and I'm going to make up a part f to this function, or to this problem, in which we're simply going to try to graph f of 2x. Since we're multiplying the input value by 2, that means we're going to have a horizontal compression. And remember, when you have a, well, stretch, but it's going to feel like a compression because we actually are going to squeeze this together. Whenever you are having a horizontal stretch or compression, the scale factor is the reciprocal of whatever you multiplied your input value by. So it's actually going to stretch it by a factor of 1/2. And if you realize that, it makes this graph real easy. If we're stretching horizontally by a scale factor of 1/2, what we're going to do is we're going to multiply the x-coordinate for each point of the graph by 1/2 in order to make that reflection. 0, 0 is going to stay the same, but right here where you have 2, 2, well, half of that x-coordinate is 1. Where you have 4, 2, half of that x-coordinate is 2. Where you have 6, 4, half of that x-coordinate is 3. Alright, those didn't fit perfectly. That's as well as I could do with the materials that I have. But you can see that I got this graph is the exact same height. It just happened in half the space horizontally that it did before. That's horizontal and vertical stretches and compressions. You are now ready to go through and stretch, translate, or reflect a graph in any way that you want to. Appreciate your attention. Hope you do well in the exercises with this. I'll see you next time.